All right. So I had you work on this compound interest formula and solving this question. Let's work through it together now. So our account, we're imagining a bank account, for example, is earning 1.23% interest. That's really, really good for a savings account these days. You know, savings accounts get terrible rates of interest these days. Compounded quarterly, that means 4 times per year. So n would be the number of compounding periods would be 4. The question is, how long will it take for the principal, the initial deposit, to double in size? You could pick a particular number for P, like 100 or 1,000 or something, but you don't have to. Why? You could just call it P or P sub 0 if you like. P sub 0, the initial amount, has to double to 2 times P sub 0. You don't even have to call it P sub 0. You could just call it P. But by doing this, I'm emphasizing it as my initial amount. Plug the other numbers in. You're going to be able to cancel the P zeros. You're going to be able to divide both sides by it. So it goes away. It doesn't matter. The interest rate of 1.23% needs to get converted to a decimal without a percent sign. That means move the decimal to the left by 2 spots. So it would be 0.0123. That's called a nominal annual interest rate because it's not actually reflecting the exact amount of interest that you get during the year. Nominal means in name only. Because of compounding, because interest is being compounded quarterly 4 times per year, you actually get a little bit more interest than this nominal rate. So that's good, I guess, that you get more instead of less. You have to divide it by the number of compounding periods n to get this quantity here, which you could think of as being what you might say it's an effective quarterly rate. Let's just go ahead and figure out what that is. 0.0123 divided by 4 is 0.003075. That's 0.3075%, a very small percentage. That would be the interest that you earn every quarter, the actual interest. But because of compounding, you actually are going to earn more than this percentage over the entire year. We're going to raise this to the n times t power, where n is 4. T is unknown. T is the thing you need to solve for. How long will it take? The unknown is t. Let's add 1 to this to simplify it a little bit. So we get, this becomes 1.003075 to the 4t power. Solve for t. Use what? We did it last week. Use logs. And again, it doesn't matter whether you use log base e or log base 10. It doesn't matter. Either way is okay. Either way will get you the right answer. They're both equivalent in difficulty here because the base is neither 10 nor e. I'll go ahead and use natural log because that is the one we want to use most. That is the one that's best for calculus. I hinted at why last week. You may not remember, but take the natural log of both sides, ln. If you do it to one side, you got to do it to the other side. Then use a property of logarithms to bring that power here down in front. This is the same as 4t natural log of 1.003075. By the way, the properties of logs you should definitely know for the exam and even be able to prove. And I do a proof in lecture 6B, I believe it is, which I will put on Moodle shortly after class today. So even if you don't watch all of lecture 6A and 6B, I'd recommend at least watching the part where I do the proof, because there could be a proof or even 2 proofs on the exam, on this first exam. There are appropriate places in a calculus course for proof. This is one of them, properties of logarithms, in my opinion. So what do we have here now? To finish, we have 4t times, these are all being multiplied, 4 times t times natural log of this thing. So divide everything by 4 times natural log of that thing so that t is isolated. I'll go ahead and put the t on the left. T then becomes natural log of 2 divided by 4 times natural log of 1.003075. Now, actually, I could have just brought the T in front. And instead of dividing by 4 there, I could have had the 4 in the power there. Either way, it'd be okay. But this is okay as well. And here's a word of good advice here. Excuse me. To maximize your partial credit on the exam problems when you have to show work, instead of just writing down the final approximation, it would be good to write down intermediate approximations, so that makes it easier for me to find your mistakes if you make a mistake. And I can give you more partial credit if you made just a small mistake instead of one small mistake instead of 2 big mistakes or something that I can't even see because you didn't write it down. So I'm going to go ahead and figure out the top and the bottom individually as a way of helping me show more work here to possibly get more partial credit if I make a mistake. 0.693147180 is the top. 4 times natural log of 1.003075 is the bottom. That's about 0.012281124. Then divide. I could retype in the 0.693 if I like. I can also do this ln of 2 again, and then divide by the previous answer. Oops, if I don't make a mistake. ln 2, divide by previous answer, about 56.4. Now you can round, right? You don't want to round too early because otherwise your errors propagate. And this will be years. Question?
Wouldn't it be easier to use the other log without?
You don't really need to. I mean, this is not log base 10 either. This is not a base 10 here either. So they really would be equivalent in difficulty. Does that make sense?
Yeah.
This is not a 10. If it were a 10 there, it'd be easier to use log base 10.
Well, I was thinking because like 2 equals 1.003075 to the 4t. That's an exponential.
Mm-hmm.
Like just switching the log, like log base 1.075 to 2 equals 4t.
Yeah, if you got a way on your calculator to do a log of some other base, you could do that. If you've got a way, but not everybody has a way to do that. Okay, so 56.4 years. People get that? Please let me know if you think I made a mistake, because I do make mistakes. And I want to catch the mistakes if I make them. Okay. A couple other comments about this formula before we go on. So this can be used to find, for example, balances on accounts. If you know the principal, you know the interest rate, you know the number of compounding periods, and you know the time, or find other things like the unknown time. It can also be thought of in a more general setting, not just in terms of bank accounts, as giving a formula that models what you could call the future value of a certain quantity. You could think of the principal P as being a certain amount of money right now, and based on a certain interest rate, you might be wondering what's its value in the future, 10 years from now. And you don't necessarily have to have a bank account to think about that kind of thing. For example, $1,000 right now might be equivalent to $2,000 20 years from now. The doubling time could be 20. And again, you don't even have to think about a bank account for that. That could be sort of a theoretical thing you think about in the context of economics, for example, and finance. Because there's something called the time value of money. People would rather have $1,000 now than $1,000 20 years from now, right? Doesn't that make sense? Even if you don't have anything to invest it in, maybe just because you'd like to spend the money right away, you'd rather have $1,000 now if somebody offered you $1,000 now versus $1,000 20 years from now. You'd take the $1,000 now. To compensate you, if you said, okay, I will wait 20 years, you better pay me $2,000 if I wait 20 years. It's sort of compensating you for having to wait. So that's what I'm trying to get at here. This formula applies in a more general setting, relating future values and present values. And I will talk about that more from time to time. And in fact, in lecture 6A, if you watch lecture 6A, I talk about present values and future values in terms of actuarial science. If you're interested in the possibility of being an actuary, you might want to watch that part. All right, main thing we should focus on today, though, is some trigonometry. You know, before you come into a calculus class, what you're mostly used to with trigonometry might be right triangles, right? SOHCAHTOA, sine is opposite over hypotenuse, is SO, S-O-H. Cosine is adjacent over hypotenuse. TOA, tangent is opposite over adjacent, right? To right triangles, you've done that kind of thing before? Should have. Maybe you're in a physics class and you have to use that all the time. That's what most people think of when they think of trigonometry. However, in a calculus class, though we do use trigonometry in that way, it's not really the most important application of trigonometry for us. A more important application, though that's my opinion, is trigonometric functions, these kinds of graphs that are used to model periodic behavior. That is probably even more important in a physics class than right triangle trigonometry. Sinusoidal graphs, these graphs that look like this, that are waves that go up and down periodically with a certain wavelength, you might call it, and a certain amplitude, are probably a more important application of trigonometry. Trigonometric functions like the cosine and sine. Let's go ahead and think about this, a problem here from section 1.5. I'm on page 43, if you want to look there in your book, where we actually have to use a sinusoidal function to do some modeling. I'm going to look at number 38 here. The depth of water in a tank oscillates sinusoidally. Okay, when you see that phrase, oscillates sinusoidally, the first thing you should think of in your mind is, oh, that means the graph of the depth versus time in this case must have this kind of shape, this oscillating kind of shape. That's what it must mean. That's what it means to oscillate sinusoidally. It doesn't mean you use the sine function. Maybe the cosine function is more convenient, but it is a sinusoid. Its smallest depth is 5.5 feet, and the largest depth is 8.5 feet. Find a possible formula for the depth of in terms of time in hours. And again, it varies once every 6 hours. What does that mean? What do you think it means to vary once every 6 hours? Go ahead. That's the period of the wave, equivalent to the wavelength. Usually you use the word period for a sinusoidal wave when the independent variable is time, a period of time, and usually use the word wavelength when the variable for the sinusoid is a length, like an actual distance in centimeters or something. Use period for time, wavelength for actual lengths, but they really mean the same thing. It's a peak-to-peak kind of distance horizontally, like from this peak to that peak, a horizontal distance. That's the same as the period or wavelength. It doesn't tell you, sometimes the problems are a little bit vague, and this is one of them. It doesn't tell you, excuse me, the depth at time zero. It doesn't say it. What that must mean is there must be infinitely many answers. You could start the depth at any time you want, or start time zero at any depth you want, might be a better way to say that. It would be simplest to either be at its average depth at t equals 0 or its maximum depth at t equals 0. Those are the simplest options, but they're not the only options. Let's start with assuming the maximum depth is at t equals 0. It's probably good to draw a graph first instead of just trying to write a formula. So make a graph like this and make your horizontal axis kind of long like that. And we can do d for depth, I guess. And well, I should have made this scale go up higher here, perhaps. The maximum depth is 8.5 feet. And the smallest depth is 5.5. So 8.5 might be right about here. And 5.5 might be right about there. And again, if we pretend, just for the sake of simplicity, that it's at the maximum depth when t equals 0, the graph is going to oscillate then like this, a sinusoid. And theoretically, the model goes on forever and ever. Though, of course, in practice, that can't be the case. So maximum depth of 8.5, minimum depth of 5.5. Can you picture what's going on here? You got a tank. The water level is going up and down. Starts up high. Evidently, somebody opens the drain, it goes down, and then somebody closes the drain and turns on the faucet, goes back up again. You know, who would do such an experiment? I don't know. It's probably more relevant to do this for something like tides instead of water in tanks. I suppose one possible application this is hinting at is the water level in like a water tower or something. You know, the water level in a water tower is going to go down during the day as water gets used faster than it goes in. And then maybe it'll go up at night as water is not used as fast. Mm-hmm. Hydroelectric dam, yeah, like the water level near the side, because they let water out of the dam, or they increase the rate at which it flows out and then decrease it. Yeah, that would be another application.
Electricity use also.
Say it again.
Electricity use does the same thing, so they have to open up much more water through electricity use goes up in the afternoon, goes down.
That's exactly right. Power usage. In fact, I think there might even be a problem about that. Yeah, number 40 is about power output for a solar cell. Lots of applications of these things. Do these kinds of graphs model these kinds of things perfectly? No. But they usually do pretty well in certain situations. One clear example where they do really well is when you have a mass attached to a spring and you pull it downward and let it go up and down. As long as there's not much friction, this will describe the displacement of the mass, this kind of graph. Excuse me, sorry. I need a drink. All right, the period is 6 hours. So that's the same as the wavelength. This horizontal distance right there is the period. Period is typically labeled with a capital T. Wavelength is typically labeled with the Greek letter lambda. Lambda looks like this. They mean the same thing, but the application is different. Time is the variable. We think about it as a period. This is 6 hours here. So you can see the scales and the axes are different. That's okay. Don't let it bother you. Why don't you, if you've done this kind of thing a lot before, maybe you think you're pretty good at it, why don't you go ahead and take 30 seconds to see if you can figure out a formula for this. If you haven't done this much or you've forgotten, I'll start giving you a hint. D is going to be a function of time. D equals f of t. Probably best to use the cosine function, leave a little space here. Leave some space in there and then plus something. Does that give you a hint about how to think about this? Probably the trickiest part is well, actually all three parts might be kind of tricky here. It's a little tricky, especially initially the amplitude might be a bit tricky. Here's one big hint. The amplitude is not 3. That distance is 3. That might make you think the amplitude is 3, but it's actually not. Might be useful to try to figure out where this line is as well. I just drew there, that purple dashed line. Okay, if you got it, good. If you've done this kind of thing a lot. If not, it's okay. The amplitude is not the distance, the vertical distance between the peak and the max and the min. It's half of that distance. So the amplitude is 1.5. That's the amplitude. It's half of the vertical distance between the highest value and the lowest value. The average of the highest value and the lowest value is the vertical shift. The regular cosine graph has an average value of 0. You've got to figure out how much it's been shifted upwards, translated upwards here by figuring out what's the average of 8.5 and 5.5. And what is it? Not 6.5, 7. Right? 8.5 plus 5.5 is 14, divided by 2 is 7. 7 is 1.5 units away from 8.5 and also from 5.5. So that's what gets added out there is the 7. Inside the parentheses of the cosine function, there's a t, but there's something in front of the t. What goes in front of the t? It's just something you probably needed to remember. It's related to the period, which is 6. If I call whatever goes there, I usually call it b. It is related to the period. It's a fraction related to the period. What goes in the numerator, the top? 2 pi. And in the denominator, the bottom goes the period, the capital T. In this case, that's 2 pi over 6, which simplifies to pi over 3. You can always check this. There's different things you can do to check it. You could plug in t equals 6, for example, and make sure you're back up to 8.5. When you replace t with 6, just think with me here, 6 times pi over 3, the 6 and the 3 cancel, the 3 completely and the 6 leaving a 2. Pi over 3 times 6 would be 2 pi. Cosine of 2 pi. 2 pi is all the way around a unit circle. You're back to where you started with. It's the same as cosine of 0, which is 1. So remembering things from trigonometry is handy instead of having to look them up or use your calculator all the time. Cosine 2 pi is 1. 1 times 1.5 is 1.5 plus 7 is 8.5. You're back up to the maximum value of 8.5 when t is 6. Are you at the minimum value when t is half the period, 3? Plug in t equals 3. Pi over 3 times 3 is pi. So 3's cancel. Cosine of pi. Pi is 180 degrees. Equivalent to that, pi is in radians. Cosine of 180 degrees is -1. Something worth remembering. -1 times 1.5 is -1.5. Plus 7 is 5.5. And you could check other values as well. You can also graph this with your calculator. This does work. It's not the only answer, actually, or at least not the only form of the answer, would be a better way to say that. There are actually other ways to write this. There's actually infinitely many different ways of writing the correct answer. They still represent the same function. They just look different. The amplitude's got to be the same, and the vertical shift has got to be the same. But whether we use a cosine or a sine could be up to you to a certain degree. No pun intended. Let's use a sine. But wait a minute, how can I use a sine if I'm at the peak when t is 0? When little t is 0? Well, you can, as long as you do a horizontal shift as well. This is the simplest answer right there. You should probably go for the simplest. But it is good to have the skill to understand the less simple, because there might be situations where you need those skills. And if I were going to use a sign here, I want to remember, first of all, that the sign of 0 is 0. At time 0, when the input is 0, the sign is at its average value. I want at time 0 for this graph to be at its peak, at its high point. If I just did pi over 3 times t here, I'm not doing pi over 3 times t, but if I did, don't write a t yet, it would be a graph that is essentially this red graph shifted to the right. By how many units? It would actually be 1.5 units to the right to get let's see, to get the graph of this function if I just use the t there. But I want the graph of this function. So I want to take a sine graph that would look like this and actually shift it to the left by 1.5 units. If I just had a sine pi over 3 times t, the graph would look like what I'm drawing here in green. That graph, to match the red graph, needs to get shifted to the left by 1.5 units. And if you recall from your content about horizontal shifts, that means replace t with t plus 1.5. Gets confusing, it's tricky, right? Do I subtract 1.5 or do I add it? You can always check it by plugging numbers in. If, for example, you plug in t equals 0 here, 0 plus 1.5 is 1.5. 1.5 times pi over 3, what would that be? Do the 1.5 and the 3 cancel? They actually can be thought of canceling. And what would you be left with in the bottom of this fraction if you thought of them that way? 2. You can cancel things that are not whole numbers here, in this case at least. 1.5 divided by 3 is 1/2. 3 divided by 1.5 is 2. I can cancel to that. This becomes, when t is 0, a pi over 2 inside the sine. Sine of pi over 2 is 1. Pi over 2 is 90 degrees. Sine of pi over 2 is 1. And 1 plus 1.5 is, or times 1.5 is 1.5, plus 7 is 8.5. It does work. You can check it. You are at the peak when t is 0. I also could have used another cosine function. I could have done 1.5 cosine. Not the same thing here. I could have taken t and subtracted 6, the period, from it as an alternative way of using the cosine function. Or added 6. The period is 6. I could subtract 6. I could add 6. I could subtract 12. I could add 12. That shifts the graph, the red graph, to the right by 6 units, which makes it be right back on top of itself. It would be the same graph because the period is 6. I mean, again, we wouldn't do this. I'm just emphasizing you can if you want. Use the simplest one. That's probably best. It's not asked for in number 38, but what if I asked you to figure out what is the earliest time when the depth is 7 feet? No, let's think something other than 7. 7.5 feet. So this is a new question. What is the earliest time when the depth is 7.5 feet? How would you solve that? Using this. Set D equal to 7.5 and solve for D. (7.5) equals f of t, solve for t. You got to isolate t. So subtract 7 from both sides. Cancel over there. 0.5 would be 1.5 times cosine of pi over 3 times t. Then divide both sides by 1.5 to isolate the cosine. 1/3 will be cosine of pi over 3 times t. It's just a coincidence that I got a 3 in both of those spots. That's just a coincidence. What should I do now? I'm trying to isolate t. Yeah, use the arccosine function, or also called inverse cosine. The arccosine name, I think, is an older name, if I recall correctly. Inverse cosine is like a newer name for this function. Inverse cosine is what calculators use. Arccosine actually is what Mathematica uses. They're the same function. You can think of it either way. And by the way, this notation here does mean inverse function. It does not mean -1 power. That is an inconsistency in math. When you write things like this, cos squared t, you actually do mean power. Cosine of t, quantity squared is what it means. But this does not mean cosine of 1/3 to the -1 power. It does not mean that. If you meant cosine of 1/3 to the -1 power, if you meant this, you'd either write that, or you'd write this, or you'd write secant 1/3. And these are not equal to, this is not equal to this. Not, capital N-O-T, not equal. I'm just emphasizing that, okay? If you've been confused about that in the past, be unconfused. They're not the same. And it's unfortunate that they're not the same. This does not mean -1 power, but we're stuck with it. But that's maybe why some people prefer saying arccosine instead of inverse cosine. ARCCOS, arccosine. On the right-hand side, you do effectively get cancellation of the cosine and the inverse cosine. Why do I say effectively? Technically speaking, the cosine function is not invertible. This function is not 1-to-1. It fails the horizontal line test spectacularly. There are horizontal lines that go through it infinitely many times, not just twice like a parabola. So it's definitely not 1-to-1. It definitely does not have an inverse function. But hey, I'm just calling this the inverse function. What am I doing? I'm only considering a piece of the cosine graph and inverting that piece. I'm restricting the domain, just like we talked about with the quadratic. And for the inverse cosine function, you always get an angle back. You can think of it as an angle, at least a quantity back between 0 and pi, always, when you use your calculator. You never get something that's not between 0 and pi. And you can only plug in numbers between -1 and 1, in fact. Unless my calculator is set to deal with complex numbers. If I try inverse cosine of to error domain. Actually, it is a little funny, like I just hinted at. If you allow complex number inputs, you actually can take inverse cosines of other kinds of numbers. But we're not doing complex numbers, so don't worry about it. Think of this as simplifying to pi over 3 times t. And therefore, now multiply both sides by 3 over pi. T is going to be in exact form 3 over pi times the inverse cosine of 1/3. Inverse cosine is right here. It's above the cosine button. I have to use the second function. 1/3. It's always between 0 and pi. The answer there for the inverse cosine. However, we need to multiply by 3 over pi. So since you have to multiply by something, you could get an answer bigger than pi or less than 0. Although 3 over pi is between 0 and 1, so we won't. Times 3 divided by pi. T is about 1.175. The units are hours. Make sure to include those. 1.175 hours. You could figure out the number of minutes by subtracting 1 and then times 60. It'd be 1 hour and about 10.5 minutes. Is what I've just done. Let's verify that. But it's fine to just leave it like this. Does that make sense looking at the graph? You should think about these things. Ask yourself, does the answer make sense? The graph can help. 7.5 is a little bit above 7. I'm trying to draw 7.5 in there. 7.5. Go over to this graph. It seems reasonable. This is 1.175 approximately. If you want to know more clearly, graph it on your calculator and use the trace function or use the root finding feature like you've been doing in the appendices. Maybe we should do that quick. I meant to show it to you in class, but haven't had time. So I'm going to go ahead and plug the function in. 1.5 cosine of pi over 3 times t is the same as pi times t, which of course is going to be an x on the calculator, divided by 3, use parentheses, plus 7. Pick a window like 0 to 6 would be a good window. And maybe 0 to 10 for the y min and y max. This should be a pretty good window. There it is. I mean, the trace is going to give you approximations. If I trace this. They were pretty close to the answer. If you also graph the line y equals 7.5, you can figure out where they intersect. Calculate. Intersect. First curve, second curve, and then a guess. And we get 1.175. You can check your answer. What if I ask for the second time when it's at 7.5? You could use the symmetry of the graph to help you. This distance here should be the same as this distance there by symmetry. So this second time, if you think about it, this distance right there is the same as the t value we got. 3 over pi times inverse cosine of 1/3. That's the 1.175. This number should be in exact form 6 minus 3 over pi times inverse cosine of 1/3. Approximately 6 minus 1.175, which would be 4.825 hours. That's the second time. The third time would be this number plus the period, plus 6. The fourth time would be this number plus the period, plus 6. So you can use the graph. You also can think about it with the unit circle. I think for the sake of time, I won't bother. So always remember the inverse cosine function only gives you one answer. The inverse cosine itself is always between 0 and pi. But then again, if you multiply it by something, then that doesn't have to be the case after multiplication, although it is in this case. Can I clarify anything here? This section also discusses the tangent function. Whose graph it's worth trying to remember to some degree. I think it's worth remembering this. The tangent function has a basic graph that looks like this, and it's got vertical asymptotes at plus or minus pi over 2. Tangent is defined to be sine divided by cosine. It's periodic, actually with period pi. These are pi over 2s here and here. And this behavior keeps repeating itself. Another vertical asymptote here at 3 pi over 2. It's got a vertical asymptotes where the cosine function is 0. It's got zeros roots at where the sine function is 0. 0, pi, 2 pi, 3 pi, etc. Goes on forever and ever. The graph of the inverse cosine function is not something we typically need to model things. But the inverse tangent is what I meant. Or the graph of the tangent function is what I meant to say. Is not something that we typically use to model things. So it's not as useful as sine and cosine in that way, though it is useful sometimes with right triangle trigonometry. However, the inverse tangent function has a graph that is more useful for applications. Tangent as it stands is not a one-to-one function. So technically speaking, it does not have an inverse function. However, if I restrict the domain, I can make it one-to-one. If I restrict the domain to just be this piece between negative pi over 2 and positive pi over 2, that piece is a one-to-one function. And the inverse tangent function, or arctangent function, is the inverse function of just that piece. Let's redraw it down here. Let me try to make this somewhat accurate here. I'm going to try to make the scales and the axes the same. Pi over 2 is about 1.57. About 1.57. It turns out that the tangent of pi over 4 is a special value. Pi over 4, which would be about 0.0785, I guess. Check that. Pi divided by 4. Yeah, close to 0.785. Is a place where the tangent value is special, it equals 1. Tangent of exactly pi over 4 equals 1 exactly, and 1 in the scale would be about there. Tangent is also an odd function. If you graph it to this side of the vertical axis, its graph to the other side of the vertical axis can be found by reflecting through the origin. Looks about like this. And I haven't made my scale on the other side, so this is still not perfect. And this is going to be -1 there. Halfway decent graph of the tangent function on the piece where we consider it to be 1-to-1, and therefore has an inverse function whose graph, if we graph it as a function of t, by like swapping the variables, is going to be the reflection of this graph across the line y equals x. One is going to be about there on the horizontal axis. The line y equals x goes about like this, or y equals t, I guess I should call it. So if I reflect this graph across that line, again, this is tricky to do. It's good to turn this at a 45-degree angle so that the y equals t line looks vertical to you. So it doesn't look vertical to me unless I move over a little bit. The graph, the inverse function, is the reflection across there. Over here, it's going to be about like that. And down here, it's going to be about like this. And instead of having vertical asymptotes at plus or minus pi/2, oh, I should have drawn this better. Scratch this out. Instead of having vertical asymptotes at plus or minus pi/2, it's going to have horizontal asymptotes there. Pi/2 here, it's got a horizontal asymptote. Negative pi/2 here, it's got a horizontal asymptote. And the interesting thing about this function and what makes it useful many times is it's actually defined for all values of t. And it's got two distinct horizontal asymptotes. That can happen. Functions can have two distinct horizontal asymptotes. Many functions, like rational functions, have just one horizontal asymptote. But you can have functions that two, and this is kind of what makes this function useful, plus the fact that it's always increasing and it's concave up before it's concave down. Those kinds of features of it make it useful for some applications in modeling functions over time, for example. Any questions? So, I'm trying to hit the most important highlights of what you find in the book. I don't have time to go through everything, but other things in these chapters are things you should know because they're things you should have learned from the past and you're just reviewing. If you need to fill in some details, some gaps, make sure you take the time to do that. Maybe by watching the lectures that will fill in some gaps, but I talk about other things as well. Maybe by watching some things on like Khan Academy or something. Okay? That's it for today. Don't forget to upload your pictures.